Hey, today we're going to discuss Chapter 12, which involves chemical bonding. We're going to look at sections 1 through 3, which involve types of chemical bonds. So first, let's look at what is a bond. A bond is a force that holds groups of two or more atoms together. And bond energy is the amount of energy required to break a bond. So the more energy required to break a bond, the stronger that bond is going to be. So it measures the strength of the bond. Sometimes electrons between bonds are not shared equally, and we're going to look at 3 different types of bonds that you can have within molecules. The first type of bond is an ionic bond. We're going to abbreviate that with IB, and it's between a metal and a nonmetal. In this bond, electrons are not shared equally at all. In fact, they're stolen by the nonmetal from the metal. Because remember, metals want to be cations, which is positively charged, and nonmetals want to be anions, which are negatively charged. The second type of bond is a covalent bond. We're going to abbreviate this with a CB. This is between two nonmetals that are exactly the same identity. So between 2 oxygens, between 2 carbons, any 2 nonmetals that are exactly the same. So in this bond, electrons are shared completely equally because the atoms involved in the bond are the same. The third type of bond is the polar covalent bond. And we're going to abbreviate this with PCB. This is also between 2 nonmetals, but they are not the same elements. So between maybe carbon and oxygen, or sulfur and oxygen, or hydrogen and sulfur. Any 2 nonmetals, but they can't be the same. In this type of bond, electrons are not shared equally. They're shared, just not equally. And this creates what's called a partial charge. And so it's this weird symbol, and it's kind of like a fancy D. It's a Greek symbol. Okay, electronegativity is involved in determining the type of bond. So even though we've talked about this a little bit, let's just review. So electronegativity is the ability of an atom in a molecule to attract shared electrons to itself. So how much can something take electrons from something else? The electronegativity is present in polar covalent bonds and ionic bonds. Because in a covalent bond, it's the same 2 elements, they don't need to take electrons from each other because they're exactly the same. Electronegativity increases as you go from left to right. So as we go across, it's going to increase. And as you can see, high is red and fluorine is red. It also decreases as we go down. So we could say that it also increases as we go up. So fluorine is our most electronegative element. And down here, radium and these dark blue ones are our least electronegative. The higher the electronegativity, the closer the shared electrons are to that atom. So fluorine is going to hold on to those, is going to steal, take those shared electrons, and they're going to spend more time with fluorine than with the other atom in the bond. The type of bond depends on the electronegativity difference. We just subtract the electronegativities of the 2 atoms, and there's a chart in your book, and I'll also give you one in class. If the difference is greater than 2, that means your bond is an ionic bond. That's usually going to be a metal and a nonmetal. If the difference is between 2 and, let's say, 0.1, then it's a polar covalent bond. So that's going to be 2 nonmetals. And if your difference is 0, that's going to be a covalent bond. So again, 2 nonmetals, but they have to be exactly the same, like 2 sulfurs. Just because a polar covalent bond has the word polar in it and has an electronegativity difference, doesn't mean that the molecule itself is polar. There's a difference between a polar bond and a polar molecule, and we'll talk more about polar molecules later on. For right now, let's talk a little bit more about bond polarity and what are called dipole moments. So a dipole moment, which we're going to abbreviate with a DM, is a partial charge, and it's represented by a center of positive charge and a center of negative charge. Within our polar covalent bond, we said electrons weren't shared equally. So that means that electrons are going to spend more time on one end of the bond than they are on the other. That spot where they spend more time is going to be negatively charged because electrons are negative. And then that other end is going to be positively charged. We indicate this dipole moment with an arrow that points toward the negative end of the molecule. So we're drawing where the electrons are going to be located most of the time. So let's look at hydrogen fluoride. Okay, so we've got hydrogen, and we draw a line to represent our bond, and here's fluorine. Now, if you remember from the chart, we said fluorine was the most electronegative element. That means it's going to pull electrons closer to it. So it's going to have that partial negative charge. Okay, remember that partial symbol? That means hydrogen is going to have a partial positive. So because our arrow is going to go toward the negative end of the molecule, our arrow is going to point toward fluorine. And I always make my other end kind of look like a plus, because it helps me remember that that's the positive end of the molecule. Any diatomic, remember diatomic means two, so any diatomic molecule that has a polar covalent bond has a dipole moment. Okay, so anything that's two nonmetals that aren't the same identity, that's a polar covalent bond, it's got a dipole moment. Covalent bonds and ionic bonds don't have dipole moments. Covalent because they're shared equally, there's no pole, and ionic because they're stolen, so they're only spending time on one end of the molecule. Okay, water is an interesting molecule because it's what we call polar. This means it can attract positive and negative ions, both, and that gives it lots of interesting properties. It can dissolve ionic materials, but it's also attracted to other water molecules really strongly, and that's because it has strong bonds. And before we go to practice, let's look at an example. So water is drawn a little bit differently, and we'll talk later about why it's drawn this way. Okay, but hydrogen has very low electronegativity, lower than oxygen. So oxygen is the partial negative. We're going to look at this bond and this bond separately. Now, because they're both hydrogen, they're going to be similar. This becomes partial positive because the oxygen is negative, and same thing with this one. That means our arrow is going to be drawn toward the oxygen in both instances. Now, the reason water is interesting is because if you have something like NaCl, and we'll talk more about ionic compounds in a bit, sodium is the positive part, chlorine is the negative part. So that means that that's positive. The hydrogen attracts to the chlorine, the oxygen attracts to the sodium, and it's able to break the sodium chloride apart, making sure that sodium ions and chlorine ions are dissociated or dissolved in the water. Here are some problems to practice on, and we'll discuss this more in class. Have a good day.